Hi. Can I start?
Yeah, great. Thanks.
Okay. Yeah. Everybody hears me. Good. Thank you. Yeah. Hello, everybody. Welcome to my talk about bring network and time together using Linux tracing. My name is Alexander Arenk. I work on the Linux distributed log manager at Red Hat, which is mainly used by the GFS2 file system, which is a cluster file system. And the GFS2 file system is using the distributed log manager to control mutual access to a shared block device across several machines. So what you can expect from this talk here is we will discuss about software to visualize the distributed log manager protocol, which is the networking protocol. I'm only using trace-cmd and the Linux kernel tracing subsystem. And I'm also using a tracing framework, which is SLOG2 SDK. It's original program for visualizing message passing interface applications, which fits to a Linux cluster, because MPI applications are mainly used also for vector computing, and the paradigm fits into it. Then the only tool that I programmed was the DLM to SLOG2, which is a bridge between the Linux trace subsystem and the trace files and to the SLOG2 tracing framework. DLM, distributed log manager, is here only an example. It can be exchanged to something else. It needs to be interpreted in a different way. And we're also using the the trace-cmd time synchronized tracing feature, which followed slides assumes that we're having this enabled. So every timeline which you show in the next slide is time synchronized. It's required. So what we have to reach our goal to visualize DLM protocol is we have a pipeline step. We at first recording our traces, then we converting them to the SLOG2 SDK framework, and then we can view them in a viewer. So, and for recording, we're using trace-cmd, the official Linux tracing tool. This generates us Linux traces which are time synchronized across machines. Then we're using the developed tool DLM2SLOG2, and this generates us SLOG2 trace format. And the SLOG2 tracing framework has a viewer named jumpshot, which can be viewed the traces. But how SLOG2 visualized traces? So they have three topologies. One is the events topology. We're having a timeline showing up in jumpshot, and then event is represented by such thing. It has a timestamp on the timeline from past to future, and somewhere on the time it occurs. Then the topology is a pin needle showing out on the timeline, and it requires one timestamp and one line ID. So the line ID is on which line it should be put on. So this is a one-to-one mapping with trace events. And then we have another topology, which are states. It's again a timeline. Then we have a rectangle on the timeline, and we have a start and a start timestamp and an end timestamp to represent an interval of some state. This requires two timestamp and one line ID. Putting everything together, we're having some kind of GANTT diagram. When we have more than one lines, we have line IDs, line 0, line 1 to representing them. We also colorize this to make a distinguish between different topologies of event and state. There's also a third topology, which is the arrow topology. This symbolized a message exchange between timelines. We're having here two timestamps for the arrow and two line IDs. And at the end, we have also a legend showing up to look up what color and what topology really means. So the Linux distributed log manager, it is, as I mentioned, it's a networking protocol. It requires a cluster manager. It is used inside a cluster, which a cluster contains nodes, which are different machines inside the cluster and they exchange messages. The distributed log manager also use asynchronous API, but this means I will show you later. And there are different log modes, but we will only look into the simple log modes, which are the readers and writers log modes, like you know from other readers writers logs, which is in DLM the parallel read and the exclusive log. And it works with log masters. That means that one machine inside the cluster, one node, owns the log. Every other node need to request need to make log request to the log master, and what this is, I will show you later also. So talking about asynchronous log API, it is different what you know before. We're using the same mentioned visualization. Here's a pin needle, which representing a log request. Then we're having a pending state. So asynchronous log API means that we have a callback, which represents us that the request is complete. So it does not block until you grant the log. You get the log granted. Then you're having a different state, exclusive log mode here, and then you can make another log request. In this case, you downgrade the log. Yes, again, the pending state, and then you are in the parallel read log, which is a reader's log state. So to compare it with local trace logging, then we have only one machine. In local logging, we have only one machine, and then the machine can have, for example, here 2 logs. And in this example, we're making logging between different CPUs. And then we're having on each CPU a timeline. Here's a log request, and it's getting the writer's log. The CPU 2 makes a log request, and then it's getting contention here because it's incompatible with the exclusive log. And then CPU 6 makes a unlock, and you are in the exclusive log state afterwards. And it goes like this. Here's also an application example that there was a write on it. And here we unlock again. Here's again in CPU 6 is again a contention, and it goes on like this. Here's an example of what will show us a bug in our log implementation because the writer's log is incompatible with the reader's log. And if we have something like this in our traces, we know that we have some bug in our implementation. I will show you in future work why this could be related into some other things which I want to investigate later. But we're correcting it, and the reader's log is compatible with other reader's log, and this looks better. There's no bug anymore. And it goes up on like this, and also with a second log. This is how local trace example works. But the main difference between local logging and DLM logging is that we don't have CPUs anymore. We have different machines, so computers, which are making logging across them. So we're having our cluster, which having machines inside, which are named nodes in our cluster nodes, and they can communicate to each other with networking communication to exchange messages. Then inside a cluster, we have a log space, and we can also have multiple more log spaces. Inside the log space, we're having logs, and then we're having the machines, not anymore the CPUs, which using the log inside, and the machines are part of the cluster. So instead of showing the CPUs here, we're having the machines, which has the node ID 1, 2, 3, and 2 is the log master. That means when one making a log request here with the pin needle, then it needs to make a message exchange with the log master, which is 2, because the master maintains the log and choose whoever grants the log currently, and there's a message exchange back. And yeah, in this state, we're having pending state because we're getting the complete handler now is our log request completed, and we are in exclusive log state. So the node 3 does the same, but yeah, it's ending there. And then you can also have a different log here. In this example, also the log master makes a request, and it's important to say that there's no message necessary because it needs to request itself. And this is also important for the future work because there's an optimization to reduce the required networking communication. So you can see that this is a hierarchy here of the cluster and log space and logs and the nodes, which I also want to talk about later more. About the SLOG2 file format, I put it here also Kshark ? Here because that's also a visualizer for traces. But I saw yesterday the talk about Perfetto, and I think maybe they also talked about scaling issues. Maybe they can take a look into the SLOG2 paper. It's not written by me. I just used the SLOG2 SDK because they solved a scaling issue with visualization of traces, because it's not yet another trace file format. It tries to solve a scaling issue, and the scaling issue is if you have your x-axis, which is our timeline, when you have a very long time record trace file, and you can imagine if you open it, then you need to read the full trace file because you will want to visualize everything, but they don't do that. The trace file in SLOG2 is built up like a tree, and you can see the level order has a different kind of level of detail. So you can imagine, like in computer games, you see in an ego perspective, things are far away from you are not very detailed, but things are close to you are very detailed, and they're doing something similar just with trace files. If you just open it, then you are in the level 0 of your tree structured trace file, and it will summarize different topology in a bigger topology. And then, and if you are in the level 0, then it doesn't not need to require the reading the full of trace file. It makes only a partial read, and if the user zooms in, it depends in which area it will be zoomed in, that it reads the next part in the tree structure trace file, and so on until you hit the level 3, and this level 3 is the most detailed view which you can get. And you can see the pin needle in one-to-one, not summarized anymore. Yeah, this is for scaling the x-axis, but what is about the y-axis? The y-axis is in our case the amount of timelines, and it does not do that. Maybe the same idea can also be adapted for the y-axis, but I'm having a problem there, which I solved. I will show you later how I solved it. Another thing in the SLOG2 file format is the YCoordMap. As I mentioned, that the DLM has a specific hierarchy, and we need to represent that into the timelines. And you can also think a lot of networking protocols has the same hierarchy structures. They have different machines with joining into something, some resource like a log space ID or something else, and or database and tables. They have also a lot of networking protocols has a hierarchy structure, and YCoordMap will put your timelines into a hierarchy order. It's a multidimensional array, only you need to provide that. And you can think about like columns for the y-axis, and these columns, which can be collapse and n-collapse, maps to the line ID. at the end. And yeah, we're using it to represent the cluster hierarchy. So how this looks like, it's very generic here. You can, the first column here is 1, which simulates the top level hierarchy. Then you have the next row, which is another 1, and then 2, but filling up such multidimensional array will help you to build a hierarchy structure, which ends at the end to the line IDs which you want to put into your hierarchy structure. And we're using it to put the timelines in a specific way that it represents the DLM hierarchy. So DLM to SLOG2, that's an application which takes as input the Linux trace files. Then it converts them. That means at first we analyzing the Linux trace files. It's written in Java because the SLOG2 SDK is written in Java. We parsing all the logs. The user has the overview about all logs which are available in the Linux trace files. And then we're providing a filtering about that the user need to provide us which logs he wants to look into. Currently, this is to provide the way of scaling the y-axis. And then we generate this log2 file. We're integrating the events and states and also the arrows, which you saw previously as I showed how SLOG2 having the different topologies, events, states, and arrows. And also we generate the YCoordMap that we have the timelines in the DLM hierarchy order. And as output, we have this log2 file. So this is how it looks like. We're having here the node ID to the recorded time synchronized trace file from trace-cmd. Then we analyzing the log. The user can see all the logs which are appearing in the trace file. Then we filter out logs which are interesting, and then we pressing up another button to generate this log2 file. So this is actually how jumpshot looks like when we open the file. This is already in the very detailed zoomed level. And we have in here at the side the legend. It's of course a little bit more complex that I showed you in the presentation how DLM works. We have a lot of more different events here. And we have also the YCoordMap. Here is the log space, which represents the DLM hierarchy order. Here we're having the log, and then we're having the nodes, and we're having the timelines. Here shown up as blue. Then we're having the events, and we're having the states, which I showed you in the presentation. And we have also the arrows, which symbolize the message exchange in DLM to see how the log exchange, the message exchange are shown up in the network. So as an example here is a non-zoomed preview. When you just open this log2 file, and this is what I meant with the case of that we have the level of detail here. The events are summarized and the user need to zoom in. It can also be zoomed in from y-axis and x-axis. And yeah, this is the as the non-zoomed preview of the SLOG2 file in jumpshot to scale on the x-axis when you have 8 hours of trace records. So I want to talk a little bit more about the problems which I overcame. So this is for the tracing the asynchronous function. We're having here the DLM log function, which is the start and the return of the function. And between of the start and the return, we have the internal handling. This is what we where we have the trace points in Linux kernel. And The problem is here that we have the complete handler, which is a callback, can occur either in this internal handling between start and return or later after return. The case 2 is not complicated to deal with it, but the case 1, we want to look more into that because, yeah, we need to have a merged DLM log event, which having the timestamp from DLM log start and the return value. We only know it at the return if there was an error or not, but yeah, it depends on the return value if there was a callback or not. Of course, when there is a callback, then we know the return value is probably successful. And yeah, the question is here how to make the DLM log merged trace event. Also, I saw yesterday that Stephen was talking about sentinels. I was looking into sentinels, but what I need to do here is a little bit a look ahead, where I need to know at the start if I can assume a callback or not, and maybe I need to look at it again. But there's some piece missing. And yesterday also Stephen was saying that he was matching it up with the PID. I'm doing that as well, but this assumes that there are no parallel. In case of Stephen's example with open, there are no parallel opens currently running, because when you have threads and open at the same time, maybe open cannot happen at the same time. I'm not sure right now, but then we require some application specific behavior in case of the sys calls. In this case, when I have an asynchronous API call, it's getting more complex to getting a merged trace event. And currently I have no problems because I have the trace files. I can look into the future, and I have also a lot of hash maps which I save and then match up again.
Alex, I hope you can hear me.
Yeah?
Yeah. This is Steve. Just when you said about the process, just want to clear up one thing about process IDs. When I say process ID, is actually in the kernel, they're really task IDs, they're thread IDs.
Yeah.
So it's matching up with per thread. So we're matched. So don't have to worry about getting confused about having a threaded program. In the kernel, there is no such thing as threads or tasks. So when it's the ID, it's actually, the matching should work for that part.
I see. So there's no problem. Thank you.
Yeah.
I currently don't have a problem. I'm also using the common PID field, which is the task ID. So far, I understood now. And then, but this is also for the asynchronous function. It is it works with the synchronized function, because in the asynchronous function it is some kind synchronized, but at the end you have the callback afterwards, and the callback is also not in the same context of the task ID. So I also currently I have not a much problem, and I assuming there that the user is using the DLM API correctly, that it doesn't do at the same time the DLM log call. And what is about live recording, because I can currently deal with it because I have the trace file. And but I would like to have, it's maybe also, that's just an idea, I don't know. It's we're having the trace points and the trace events difference, and so far I understood that trace events are instances of the trace point, and maybe we can put some trace event handle into it, a unique number where I can recognize, these two trace events, they belong to each other, and we knowing from the semantic as they was introduced as trace points that we need to match them up later. Because the trace point, they don't know the semantic about that these trace points, they have a connection to each other. And yeah, I can put maybe something like that on the application layer, but the application layer doesn't give me right now the necessary information that I know this DLM log start belongs to this complete handler and so on. I don't have that currently. Another idea is Traceevent classification. I name it like this.
Yeah, Alex, again, this is Steve again. I was just about the, so you need to get 2 trace event points that are basically a way to match the 2 by fields.
Yes.
I mean, that's...
the fields are not, currently I don't have a field which they can be matched up.
Wait, so
the application doesn't tell me that.
So there's no, you have 2, the problem is you have 2 events where there's no field that actually would match between the 2 events, or?
Yeah, the currently, the asynchronous function currently works like this, that you put a callback into the DLM logs function, and then it occurs, but you don't know which, it was probably the last, only the application knows. It depends on the application handling that it match up with the DLM log start. And currently, we don't have this in DLM log API that you can match this.
Oh, so it's a DLM log. Yeah, so you have to add it to your API then.
Yeah.
Okay.
Yeah.
Just want to confirm.
We don't have something like a request ID currently, but we're thinking about to add something like that.
Okay.
Then we can match it up with the complete handler and the DLM log. Yeah.
Thank you.
Yeah. So, but I don't know. For example, there's a lot in the Linux kernel. There's a lot of bus API. Bus API has always some asynchronous function and synchronized function. Synchronized function are not they're blocking, but the asynchronous function, they work like this. And I think, for example, SPI async, they don't have something like that as well, where you cannot put know before. It depends on the maybe on the application handling how they match it up again. And there's a void data pointer where you can pass, and then they do something like that. But in the SPI async, I think you can also not know which one was it. So another idea is trace event classification, because you remember the DLM hierarchy, which is the line IDs, which I have at the end, and I record a lot of trace events, and according to trace event fields which I have, so in trace point we making the declaration of the log space ID, the log identifier, and so on. And when I have the trace event, then I'm looking at these fields, and I need to build a hash value around them, because I need to put them into different timelines. And this is what I name classification, because the name, it reminds me of the Linux traffic control subsystem. They're doing something similar with networking, and it's very generic there. You classify your networking flows, and which they're coming into your networking interface, and then you can run action on it. One action is to put a number on this buffer. This is something what I would like to have. Another action is simply drop. You can build firewalls with it. And yeah, I need to classify trace event fields. And I'm currently doing that on the application layer. My current question is it different than trace filter? If I can run different trace filter at the same time, and it gives me somehow in a separate buffer per filter, then it's something like classification. But what I'm currently doing is, here are the DLM functions. Please record them for me, and I make the classification in my application. So I would like to move it out of my application and make it somehow possible in trace-cmd or something, lib trace-cmd, that yeah, I'm pretty sure some other people can also use it. And my current solutions also have some memory issues because I put them into some hashes. And yeah, future work. The one thing what I mentioned before, I want the two problems with where maybe sentinels are the right thing to do, but there's some missing piece maybe, or I need to look at it again. I want to move things out of my application to move it more into the Linux community software, tracing community software. And another future work besides debugging, what I'm using currently for it, is continuous kernel integration. We're having a log torture tests, and then we're checking for incompatible log modes, which I showed you before with the exclusive log and the reader's log at the same time. If we see that in the tracing files, I can build some verifier tools, which tells me, oh, there was no incompatible log mode, or there was a compatible, and everything was compatible. We can make some automatic testing with it. And yeah, this is a very important test for DLM, because otherwise the whole DLM subsystem is broken and the main feature does not work. And another thing is, for example, one-time kernel optimization, which I said with the logmaster, that the logmaster, when one node makes a log request, and then it's good to switching this node to the logmaster, because it does not need to generate a lot of networking messages, and we can predict it and switch to logmaster. I don't know if tracing here is the right thing to do. We can separate the networking traffic into control and data paths, and the control paths making the time synchronized tracing, which also need to require to be in a live record, and then we're having our overview about all the logging behaviors in the cluster. And then we can switch, we can put them, we can say, hey, here at this time, please next time switch to logmaster before you're doing log requests. And also another thing that I came in around with networking queues. QDisk in Linux, they only have a local view. You can run something in user space, a daemon, to make the time synchronized traces, and then making switching kernel parameters to make your networking flows different. And SKB mark is something like, it's what I say, that you need to classify your networking flows and then putting a number to it, which is your unique identifier in your cluster, in a distributed network then. Yeah, and that was, yeah, thank you for your attention. And yeah, I have published everything on my GitLab page here. Yeah, thanks.
I don't know if you could hear, everyone applauded because the talk was great. If we have time to take questions, just remember that with a remote speaker, you really need to speak into the mic. Cool. Any questions?
Alex, actually, it's not a question. It's just a comment. But if for some of those issues that you brought up with the question at the end, we probably should have a one-on-one or something. Set up something so in the future we could discuss some of your issues you have. Okay.
Okay. Thank you. Thank you. I appreciate it.
Another question?
Your talk about asynchronous operations is really interesting, and I think from tracing any kind of non-synchronous client is a really cool and deep topic. I don't actually have a question, but I think we might want to have an unconference about tracing asynchronous operations in general, because I'm sure there's lots of interesting strategies. Thread ID is a great one if everything is based on a thread, but there's other primitives that you may need to integrate with as well.
Yeah, I think I'm not the only guy in the world which running first time into this problem about tracing asynchronous functions.
Yeah, so this is a thing both on in Android. This used to be in atrace. The application would require to provide like some sort of cookie, which is like a unique ID with like request. It's basically the same thing as a request ID. These days, Perfetto, the SDK, we make it so that you emit like a track ID, which I guess is the equivalent of your timeline, which is like a track is a timeline in Perfetto terminology. And so on that track, we enforce that everything is a track is a way of generalizing a thread, and so like it can be cross-threaded, but within a track things are synchronous, and so that's like a different way of solving like a similar problem. But instead of having like only one level of nesting, you can have like nested slices as long as you were sure that they were synchronous with respect to the track, but not necessarily with respect to threads or etc. So there, yeah, like Perfetto has some tools to solve this problem. Especially this comes from Chrome days, really, where Chrome does a lot of cross-thread tasks, which have some synchronicity to them.
Yeah.
Cool.
The main thing in DLM is that the callback, it is occurring on a completely different PID also. They get scheduled around. And yeah.
Cool. Any more questions? Okay. Thanks again to Alex for joining us remotely for their talk.
Yeah.